Let's start one short video for chemical equilibrium. So first, how to indicate equilibrium for any reversible reaction. There are two conditions. The first graph related to concentration versus time. So where concentration versus time, if you observe, at equilibrium concentration equals to constant in this graph. So this is how the equilibrium we can represent. The second graph, also another way to represent same equilibrium, where concentrations are constant as well as equal. So exactly concentrations are equal and also constant. Coming to the next, as like first one, here concentrations alone constant but not equal. Equal means these two will touch each other. So these are the three ways to represent equilibrium. Coming to rate versus time. At equilibrium, rate of forward reaction equals to rate of backward reaction. So that rate means speed of forward reaction exactly equals to speed of backward reaction. It's not constant, it is equal. So that these two will not be represented for equilibrium state when rate versus time is given. Hope it is clear. If you have still doubt, you can watch full video that I am going to make. So coming to the second one called as law of mass action. So here rate of the reaction is directly proportional to active mass of the reactants raised to the power of stoichiometric coefficients. So what is that? If you take AA plus BB gives rise to CC plus DD. Here small ABCD are coefficients of reactants and products respectively. Capital 1 are reactants and products. So according to the law of mass action, so this is called as forward reaction. Constant we can write it as Kf, and backward reaction constant we can write it as Kb. Rf is directly proportional to concentration of reactants with powers of coefficients or raised to the power of coefficients. So Rf equals to, removing proportionality and writing Kf, A power A and B power B, and same way you can write for backward reaction. So here active mass is nothing but concentration only for concentration. So you can write it as number of moles per liter or volume of the solution. Suppose if gases are there, gases is active mass of gases is nothing but pressure of the gases. Simple as concentration only. Or molarity also we can write it. And here we have got Kf and Kb. So from these two you can write as equilibrium constant, which is Kc. So it is the ratio of Kf to Kb, that we can write it as concentration of products by concentration of reactants, or product of product concentration to product of reactant concentration, as like this. And we can write for pure solids and liquids, active mass equals to 1, because their concentration doesn't change during the reaction. Coming to next units of Kc equals to mole per liter whole power delta Mg. Delta Mg is nothing but C plus D minus A plus B from the above equation. Means product gas moles minus sum of the reactant gas moles. So this is delta Ng. Same way we can write Kp, same equilibrium constant with respect to partial pressure. Representation is remain same. Product of reactant concentration with respect to partial pressures. This is how we can represent. This is Kp and this is Kc. So we can make a relation between them. Kp and Kc relation is Kp equals to Kc into RT whole power delta Ng. So with respect to Kp units equals to Atm power delta Ng. Suppose if you take all gases and concentration, if you represent with pressures, then we can indicate this way. Kp units are Atm power delta Ng. Similarly, relation between Kp and Kc, Kp if it is Kp greater than Kc, where delta Ng is positive or greater than 0. Kp is less than Kc, where delta Ng is less than 0, means negative, and Kp equals to Kc, where delta Ng equals to 0. And there is one more case, that is, so if you take temperature is 12 kelvins, then also Kp equals to Kc. What does it mean? Because R value is 0.0821, which can be written as 1 by 12, so that Kp equals to Kc into 1 by 12 into 12 if you take, so 12 gets cancelled, and then what is the result? Kp equals to Kc. So this is how we can write the different conditions for the Kp and Kc. Hope it is clear. Next one. So applications of K. So here K increases, means Kc increases, product considered as more stable, because Kc is nothing but products by reactants. K increases, more products means more stable products. K decreases, reactant stable, because K we can write it as product of product concentration by product of reactant concentration. And then Kc mainly depends on two factors. One is temperature factor, the another one is stoichiometry of the reaction. Stoichiometry of the reaction. So first condition, temperature. This is called as van 't Hoff equation, log K2 by K1 equals to delta H vaporization by 2.303 R into 1 by T1 minus 1 by T2. So here delta H is the enthalpy heat of the reaction. R we can write it as 8.314, which is nothing but 25 by 3 joule per mole Kelvin, and R calorie value is 2 calories, 1.987. We just take calorie per mole Kelvin. So here endothermic reaction means delta H will be positive, then T1 less than T2 and K1 less than K2, and temperature increases, K also increases in case of endothermic. But in exothermic, delta H equals to negative and T1 less than T2, and K2 is inversely related to this K1. So K1 greater than K2 and T increases, K decreases for exothermic. So stoichiometric is more important here. Most of the times questions asked here. So different cases we can write. Case 1. So reactants converted into products. Then let us take this is K1 here products, if it is converted back to reactant, which is K2. So what can be the relation between K1 and K2? K2 equals to 1 by K1. Why? Because K is nothing but products by reactants, just reverse of that, or inverse or reciprocal of it. K2 we can write it as just R is converted into P and A are converted into AP. Suppose if you change the stoichiometric ratio or stoichiometry, then K1, K2, so K2 equals to K1 whole power A. Whatever value we took, that will be at power. Same way case 3. So reactants converted into products. So A, here S converted into T, and R plus S gives rise to P plus T if you take. So what you can write is, this is, let us take K1, K2 and K3. So what you can write, K3 equals to K1 into K2. If you want, you can see here K1 is nothing but what? P by R. K2 is nothing but T by S. And now K3 you can write it as K1 into K2. So K1 is what here? P by R into T by S. So here, so what is the K3 from this? Products by reactants, right? So which is same as this one. So these are the ways to write it, and different way also they may ask questions. So if you want a detailed conceptual explanation, I'm going to make long video, so you can watch that long video completely and with the different lectures. And we also discuss a lot of questions based on this, so just you can watch complete video for more clarity. So degree of dissociation, we can write it as DOD. It can be written as number of moles dissociated by number initial moles taken. So if it is strong electrolyte, whatever moles we taken, that completely dissociates, so that degree of dissociation is 1 for strong electrolytes. So different cases we can write for the students. This is most important. So here A converted into B. So initial moles are 2 and 0 we took, which is called as initial moles. And number of moles at equilibrium we can write it as, so suppose X amount of or X moles of B is formed, then that is from 2, right? So that resultant moles of A at equilibrium is 2 minus X. So what is DOD here? DOD of A, which is equals to, so number of moles dissociated is X, right? X by number of moles taken initially is 2. So that is the DOD for A. So 2 minus 2 is the initial mole, so 2 minus change is X. Suppose if the coefficients are changes, how to take or how to write DOD? So here 2A converted into B. So here initial moles are 2 and 0. So here number of moles at equilibrium is, this is X moles are formed, 2 minus 2X we have to take. This stoichiometry is this one. So 2 minus 2X and X. So DOD of A here is, A is X by, sorry, the change is 2X, right? 2X by 2, which is nothing but X. This is how we can write it DOD for this case. So same way you can write case 3. So case 3 is 2A plus 2B gives rise to 3C. So initial moles are 2, 3 and this will be taken as 0. So number of moles at equilibrium we can write it as, so here 3X, because coefficient you have to write here. So here what you can write, 3 is the initial mole, so 3 minus 2 is the stoichiometry and change is X. So same way 2 minus 2X. So DOD, how to write it for particular one? DOD of A equals to 2X by 2, because change is this and initial moles are 2. So same way DOD of B equals to 2X by 3. That's how we can indicate DOD for A and B in this equation. We can also write same thing for different examples. We can write case 5 with example N2 plus 3H2 gives rise to 2NH3. So initial moles are this one. Let us take 5, 8 and 0. So number of moles at equilibrium is, so 5 minus x, 8 minus 3x, and this will be 2x. So DOD of N2 equals to x by 5, DOD of H2 equals to 3x by 8. This is how we can write it, DOD for different examples. So here x we can write with stoichiometry whatever is given, and initial moles also what is given, that we can take it. And most important is next one, applications of DOD. From here only questions are possible to ask more. Applications of DOD, most important. So find equilibrium constants with the DOD. So calculate Kc. So here A plus B gas gives rise to C. So here initial moles we can take it as A, B and 0, and the number of moles at equilibrium will be change. Let us take x. So A minus x, because coefficients everywhere 1 1, so that B minus x, and concentration at equilibrium we can write it, concentration is nothing but number of moles by volume, so that A minus x by V and B minus x by V and x by V. So here Kc, how can we write it? So Kc is nothing but product concentration by reactant concentration, so this that we can write it here. So x by V by A minus x by V into B minus x by V. This is how we can write it, equilibrium constant. Similarly, how to represent Kp for this? So representation of Kp, this is also most important. So same equation you can take, A plus B gives rise to C, all are in gases. So let us take initial moles are, this is A, this is B and this is 0. So equilibrium number of moles will be, x is the change, so A minus x, B minus x, here coefficients are 1, so just that 1x we are writing. So here different term will come, that is equilibrium, mole fraction at equilibrium, that is moles of this A by total moles. If we add total moles, how can we get it? Total moles equals to A minus x plus B minus x plus x. So we can write it as A plus bx. So A plus B minus x. This is the, so A plus B minus x is the total moles. Similarly, B minus x by A plus B minus x, and here x by A plus B minus x. This is the overall what is mole fractions of equilibrium. Now partial pressure of equilibrium, how to write it? So here A minus x by mole fraction of A minus x by A plus B minus x into total pressure is P. Similarly, B minus x by A plus B minus x into total pressure as like this. So x into P by A plus B minus x. This is how we can write it. P equilibrium means pressure at equilibrium, partial pressure at equilibrium, Kp equals to xp by A plus B minus x. So products by reactants only, nothing else. So products is this, reactants are A minus x by A plus B minus x into P. Same way B minus x by A plus B minus x into P. This is the overall what is Kp, and as it is you can follow to solve any question which related to Kp or Kc. So this is one more very important. Just need to write equilibrium, later we can convert it into partial pressure with mole fraction. mole fraction at equilibrium you should write, then you can convert into partial pressures. Later you can write it for Kp. Next one, relation between DOD and vapor density. You can write alpha equals to D minus small d by small d into n minus 1. Here n is not equals to 1. So here alpha is DOD only, degree of dissociation. D is vapor density of reactant, and vapor Vd equals to, that is capital D. So how can we write molecular weight of reactant by 2, and small d equals to vapor density of reaction mixture. This is the formula for the relation between DOD and vapor density. So vapor density equals to capital D equals to molecular weight of reactant by 2. And finally we can write Le Chatelier principle. Le Chatelier principle. So here, so if a system at equilibrium, then if it disturb by changing any one of this factor, the system readjusts itself by nullifying the changed factor. Suppose if you increase concentration, that will nullifies by readjusting the equilibrium, is nothing but Le Chatelier principle. So whatever disturbance we make for the equilibrium, that will nullifies by readjusting the position of equilibrium, is nothing but Le Chatelier principle. So very simple. So we can see the factors one by one principle. So factors we can discuss one by one. The concentration factor. If we increase reactant concentration, then the forward reaction increases, because if the forward reaction increases, the increased reactant concentration decreases. That is how the new equilibrium will re-establish, is nothing but Le Chatelier principle. We can also say this point, either by increasing reactant concentration or decreasing product concentration, the forward reaction is favorable. Same way, product concentration increase or reactant concentration decrease, backward reaction is favorable. That's how the new equilibrium is going to re-establish. Coming to second factor, effect of pressure. So if you take any one of the equation, that N2 plus 3H2 gives rise to 2NH3. So if you increase the, so let us take the reaction is at equilibrium. Now I increased pressure at the equilibrium. So if I increase pressure at the equilibrium, wherever more reactant, more number of moles are there, that will collide more. So at reactant side, total moles are 4, 1 nitrogen mole and 3 hydrogens. So here only 2. When we increase pressure over equilibrium, wherever more moles are there, that will collide more, so that the reaction moves towards forward direction, and the increased pressure nullifies and re-establish the new equilibrium. That's how pressure effect we can discuss with respect to collision theory. So here we can tell this. So delta Ng value is greater than 0. Which reaction is favorable? So for this delta Ng value is what? Product number of moles of gases minus reactant number of moles of gases. So 3 plus 1, which is nothing but 2 minus 4 equals to minus 2. So if delta Ng is less than 0, forward reaction is favorable by increasing pressure. Forward reaction favorable. And same way delta Ng is less than 0, backward reaction is favorable. And delta Ng equals to 0 means, so no change or no effect of pressure, no impact of pressure. So coming to the next, effect of volume is just opposite to this, because pressure is inversely proportional to volume. So delta Ng is less than 0 means backward reaction possible. Delta Ng is greater than 0, forward reaction is possible. And delta Ng equals to 0 means no change. A reaction, just assume A converted into B plus energy. So if I increase temperature over this equilibrium reaction, the backward reaction is possible because backward reaction is endothermic. What is meaning of that? If I increase temperature, since backward reaction happens with energy, so that backward reaction or endothermic reaction is favorable by increasing temperature. Otherwise, like by decreasing temperature, what happens is forward reaction is favorable because forward reaction is exothermic, means no need any energy. So simple, if reaction is at equilibrium over increasing temperature, whichever side endothermic is there, that reaction dominates. Suppose if you remove or if you decrease the temperature of reaction mixture and the reaction moves or the equilibrium moves towards exothermic side, that's how the temperature is going to have impact. Temperature effect can discuss. And catalyst doesn't affect the equilibrium, just it will fast up the position of equilibrium, means it reaches equilibrium position fast by increasing catalyst or by putting catalyst in the reaction mixture. And by addition of inert gas addition, so here two cases. So at constant volume doesn't affect the equilibrium. Suppose at constant pressure, so volume will change. Accordingly, the reaction moves. So reaction will shift in that direction where number of moles increases. So volume factor, whatever we have discussed earlier, the same thing can apply for this. So these are the factors affecting over the equilibrium or Le Chatelier principle. So this is just like formula sheet. So the complete video I am going to do, just you can watch full video to get full clarity. This is like just before board exams and before NEET and other competitive exam, just like one short video for equilibrium, chemical equilibrium. After this I am going to do ionic equilibrium, so don't miss, that is most important than this.